Shipping containers move quietly around the world, usually unnoticed, following standards that were agreed upon many decades ago. The familiar metal boxes that sit on ships, trains, and trucks share common dimensions, attachment points, and weight limits that were defined to avoid confusion and delay. Before these agreements, cargo was handled in loose pieces, packed in sacks, barrels, and wooden crates, each with its own size and shape. Ports were crowded with workers lifting items by hand or with small cranes, and every transfer between ship, rail, and truck required new loading and unloading. Over time, this led to congestion, damage, and uncertainty in delivery times, especially as trade increased across oceans and continents. The idea of using standardized containers appeared gradually, first in small experiments by rail companies and regional shipping lines. These early containers did not share common standards, so they could not move easily from one region or company to another. Some were short, some were tall, and the methods used to lift them were often incompatible. It became clear that a shared system was needed, one that could be understood and applied in any port in any country. That need eventually led to formal international standards, defined through committees, documents, and many technical discussions. Among these standards, ISO 668 became one of the core references. It describes the classification, external dimensions, and maximum gross masses for a family of freight containers used in global transport. The text of that standard may seem dry, but it provides a stable foundation that allows containers from thousands of manufacturers to fit together on ships, trains, and trailers without adjustment. As a result, today's containers can travel for years across long chains of handling equipment, fitting neatly into regularly spaced patterns like blocks in a simple, repeating structure. The path toward container standardization began in the mid-20th century, when shipping companies faced rising volumes of goods and rising labor costs. Loading breakbulk cargo piece by piece had become slow and unpredictable, and delays at ports could extend for days. Some operators started experimenting with large boxes that could be lifted as a single unit, keeping the cargo inside undisturbed. One of the most influential figures in this story was Malcolm McLean, a trucking entrepreneur who saw that sealed containers could move from a truck chassis onto a ship without opening and repacking. Early services used containers that were practical for specific fleets, but not designed with wider compatibility in mind. Different companies used different lengths, widths, and locking methods, which created barriers when trying to interchange equipment. National standards bodies and international organizations began to study the issue, realizing that an agreed system could support smoother trade. The International Organization for Standardization, known as ISO, formed technical committees to create shared specifications for freight containers used in international transport. Engineers, shipping lines, port authorities, and manufacturers contributed data and proposals. They compared existing container sizes, looked at typical cargo weights, and studied how ships, wagons, and chassis could be designed around a few main sizes. Through this systematic process, they moved away from scattered proprietary designs and toward a family of defined series. The result was a set of ISO standards that gradually shaped the modern container fleet, including ISO 668 for dimensions and weights. This standard did not appear overnight. It was refined over several years, with amendments and revisions as experience accumulated. By the late 1960s and early 1970s, its influence could be clearly seen on new container ships and on the layouts of emerging container terminals, which were built around predictable container footprints. ISO 6668 focuses on the classification and main external dimensions of what it calls Series 1 freight containers. These containers are intended for general cargo in international transport, and they form the most recognizable shapes seen in container yards. The standard defines various nominal lengths, but the most widely used are the 20-foot and 40-foot containers, commonly called 20-foot and 40-foot units in everyday operations. Width is standardized at about 8 feet across, allowing containers to fit side by side on ship decks and on standard rail wagons. Height is typically 8 feet 6 inches for a standard container, with a higher version known as high cube at 9 feet 6 inches, giving extra internal volume for lighter, bulky cargo. ISO 6668 sets maximum gross masses for each size code, giving clear limits for how heavy a loaded container may be. These limits are important for safety because ships, cranes, and vehicles must be designed to handle known maximum weights. The standard also ensures that the positions of corner fittings, sometimes called corner castings, are consistent from one container to another. These small reinforced blocks at each corner are where spreaders, twist locks, and stacking gear attach. Because their positions are carefully specified, cranes can lift any compliant container using the same equipment, and containers can be stacked securely on top of each other. ISO 668 does not describe every construction detail, but it establishes the outer envelope and key strength-related values that others can design around. Manufacturers use this envelope to design walls, floors, and frames that meet both the dimensional and structural requirements. Ship designers use it to calculate how many containers can be stowed in a given bay. Truck and rail designers use it to match deck lengths and axle layouts to container footprints, which simplifies planning and loading routines. Over time, the standardized container became more than just a box. It became a basic unit for planning transport capacity. Ports measure their throughput in 20-foot equivalent units, known as TEU, which relate directly to the length series defined in ISO 668. A single 20-foot container counts as 1 TEU, while a 40-foot container counts as 2 TEU. Terminals use this measure to estimate yard space, crane cycles, and berth demand. The repeated external dimensions also allow ship designers to draw cargo plans made up of simple rows and tiers. They can treat each slot as a rectangle with fixed dimensions, filling them with containers in regular patterns. This regularity is only possible because containers built in different factories and used by different carriers share the same reference sizes. Even when new features are added, such as side doors or internal linings, the outer envelope remains within the ISO limits so that handling is unaffected. The daily routine of container handling depends on this predictability. Crane operators know that each time they lower a spreader, the corner fittings will be in the same relative position. Yard planners know that stacking 3 or 4 high will produce stable columns of equal footprint. Train assembly crews know that a given wagon can accept either one large container or 2 smaller ones without confusion. All of this reduces the number of decisions that must be made at each step. Instead of treating each load as a unique object, equipment can treat containers as identical modules with only a few key differences, such as weight and destination. The result is a quieter process with fewer adjustments during loading and unloading, and fewer unexpected delays. ISO 6668 sits alongside other container standards that together shape the full system of ISO containerization. For example, ISO 1161 specifies the corner fittings that are used for lifting and securing containers. ISO 1496 covers the testing and rating of containers for different types of cargo, including general purpose, insulated, refrigerated, and tank units. ISO 3874 describes handling and securing methods. While each standard has its own scope, they are designed to be consistent with one another. ISO 6668 defines the series and sizes, while other standards fill in additional structural and operational details. Together, they ensure that a container built on one continent can be carried, stacked, and secured using equipment designed on another. The term ISO containerization is sometimes used to describe this entire framework of standardized containers, corner fittings, twist locks, spreaders, and related handling practices. It distinguishes these containers from non-ISO units, such as small domestic moving boxes or specialized industrial modules that do not follow globally recognized dimensions. In practice, ISO containerization means that a shipping line can accept containers from many different customers and move them through a shared infrastructure with minimal customization. Ports can invest in cranes and automated stacking systems once and use them for many years, confident that future containers will continue to match the same dimensional patterns. This stability has encouraged large-scale investment in container terminals, inland depots, and intermodal rail lines. All rely on the idea that the physical interface between container and equipment will remain stable over long periods, guided by revisions to the standards that are careful and incremental rather than abrupt. The introduction of standardized containers changed how ports were designed and operated. Traditional breakbulk piers required large covered sheds for storing loose cargo while it waited to be loaded or collected. With containerization, much of the cargo remained sealed inside the container from origin to destination, reducing the need for intermediate warehousing at the quayside. Instead, ports built open yards with marked lanes and stacking areas sized for container footprints. Cranes with long booms and specialized spreaders replaced many smaller cranes and manual hoists. Horizontal transport within the port shifted toward vehicles designed to carry one or more containers at the standard dimensions set by ISO 668. Planners could map out yard capacity using simple grids, each cell representing a container slot. In cold or hot climates, refrigerated containers could be placed in areas with power outlets, but their external size still followed the same basic pattern, so they could circulate through the same handling system. This allowed container terminals to handle many cargo types without changing the main layout. Over the years, as ships grew larger, ports deepened berths and extended quays, but the basic unit in their calculations remained the standardized container. Bridge cranes were scaled to span wider beams and taller stacks, yet their spreaders still matched the same set of corner-fitting positions. This gradual evolution meant that container handling became a routine, almost repetitive activity, built around predictable, fixed shapes. The standards that govern those shapes rarely attract attention, yet they influence the rhythm of loading and unloading at nearly every major seaport in the world. Standardization also influenced inland transportation networks. Rail operators developed flat wagons and well cars sized to match the lengths set out in ISO 668. Some wagons carry a single 40-foot container, while others carry two 20-foot containers coupled together, fitting within the same overall length. Road trailers were likewise designed with decks that correspond to these container lengths, often with twist locks or pins positioned to engage the corner fittings. Because height and width are limited by road and rail clearance profiles, the consistent container dimensions help ensure that combined loads pass safely under bridges and through tunnels. Intermodal terminals inland, sometimes called dry ports, handle containers arriving by rail and departing by road, or the other way around. They can operate efficiently because each container, regardless of owner, has the same essential external shape. Equipment such as reach stackers and straddle carriers can lift and move them without adjustment for unique sizes. Even where short regional variations occur, the core ISO sizes dominate the international movements. This uniformity simplifies planning for cargo owners as well. A manufacturer can load goods into a 20-foot or 40-foot container, knowing that it will fit into ships, trains, and trucks across many countries without repacking. Freight forwarders and logistics planners can count container slots rather than measuring each load individually. This reduces sources of uncertainty and helps build long chains of movement that extend from factory or warehouse to distant markets, all based on a limited and clearly defined set of container forms. Within the framework of ISO containerization, several specialized container types evolved while still respecting the main dimensional series. Open-top containers allow large or awkward cargo to be loaded from above, using cranes, yet their base footprint and corner fittings follow ISO 668. Flat racks provide strong end structures and a flat bed for heavy or oversized machinery, again matching the same length and width as standard units. Tank containers carry liquids in a cylindrical tank mounted within a shallow frame, but from the outside, the length and corner fitting positions align with standard containers. Refrigerated containers, often called reefers, include insulation and refrigeration machinery, but share the same external pattern, allowing them to be stacked and secured alongside ordinary dry containers. There are also half-height containers for dense bulk materials and bulk containers with roof openings for granular cargo. In each case, standardization at the external level supports diversity at the internal level. The ISO documents give enough flexibility for these variants, while preserving the common interface for handling and stacking. This approach allows shipping companies to carry many different types of goods without redesigning ships or terminals for each new cargo. Operators can mix and match container types on the same vessel and in the same yard, confident that the main dimensions and corner positions will remain consistent. Over the decades, this quiet balance between variation and uniformity has allowed container fleets to adapt to changing trade patterns and commodity mixes, while still fitting neatly into the original grid set out by ISO 668 and its companion standards. The history of ISO 668 itself includes several revisions as experience with containers accumulated. Early versions focused on establishing a core range of lengths, heights, and strengths suitable for shipboard use at the time. As container ships grew larger and container stacks on deck became higher, the need for clear rules on maximum gross masses became more important. Revisions adjusted some values and clarified definitions to match real-world practice. At the same time, feedback from manufacturers and operators led to refinements in tolerances, ensuring that containers built in different factories would still align accurately in stacking and securing systems. Some proposed sizes were considered but did not gain wide adoption, as the industry converged on the 20-foot and 40-foot as the primary global standards, with additional use of high cube variants. Each revision of the standard went through drafting, commenting, and voting stages within the ISO Technical Committee, involving experts from different countries. The goal remained to preserve compatibility with existing fleets while offering guidance for new production. Because containers have long service lives, abrupt changes could have disrupted existing operations, so the process favored steady, cautious modification. The final documents appear as precise tables and diagrams, but behind them lies a long history of practical experience, measurements, and field observations from ports, depots, and ships. Over time, the text of ISO 668 has become a reference that designers consult routinely, much like a simple, well-established formula. It quietly shapes everyday design decisions, guiding how new containers are ordered, how spreaders are built, and how cargo space is allocated on new vessels. The impact of standardized containers extended beyond the physical movement of goods to broader economic patterns. Lower handling costs and reduced damage made it more practical to ship manufactured products over long distances. Factories could specialize, knowing that containers would carry their output reliably to ports and consumers elsewhere. Distribution centers and warehouses were designed around container receiving and dispatch areas, often with loading docks matched to container floor heights. Ports that embraced containerization early gained advantages, while others had to catch up, upgrading infrastructure to handle the new mode. Despite these changes, the underlying technical basis remained a set of stable standards. ISO containerization simplified the interface between many parties in the supply chain. A container could be passed from a truck operator to a rail carrier to an ocean carrier, each using standardized documentation and physical equipment. This reduced the number of handovers where cargo was exposed or repacked. As a result, cargo security and predictability improved. Insurance practices and freight rates adjusted in response, with containers treated as predictable, measurable units. Even in times of disruption, such as congestion or schedule changes, the standardized nature of containers allows for relatively straightforward reallocation of equipment and rerouting of shipments. Planners can shift a container to a different ship or rail service without worrying about custom dimensions. All of this reflects how a set of technical documents, including ISO 668, can shape large systems quietly over many years, turning what once was complex and irregular into something more modular and manageable. While standardized containers simplify many aspects of global trade, they also introduce limitations and trade-offs. The fixed dimensions defined by ISO 668 do not suit every type of cargo, especially very large, very small, or extremely heavy items. Some goods still move outside containers, using specialized ships or bulk carriers. However, the broad usefulness of containers means that a large share of manufactured products and packaged goods now travel in these standard units. Infrastructure investments tend to follow these dominant flows, reinforcing the position of ISO containerization as the main framework for general cargo. As technology evolves, new ideas continue to appear, such as automated container handling, advanced tracking systems, and improved materials for container construction. Yet even in these developments, the external forms often remain consistent with the familiar Series 1 dimensions and masses. Automation systems, for example, rely on fixed sizes to program robotic stacking and guided vehicles. Tracking devices are designed to fit within the structure of the container without changing its external profile. In this way, innovation can proceed within the stable outline provided by the standards. The quiet persistence of these dimensions can be seen in container yards, where different colors and conditions mix, but the lengths and heights remain uniform. Old and new containers stand side by side, connected by the same corner fittings and lifted by the same spreaders. The standards that defined them earlier continue to guide their use, long after their original drafting. As the story of standardization and the history of shipping containers continues, ISO 668 remains one of the central references for the physical form of containers in international trade. It works together with related standards in the ISO containerization framework to create a stable, predictable set of building blocks for global logistics. Decades after the first experiments, containers still move quietly through ports, inland depots, and distribution centers, following the same basic rules of size, weight, and connection points. Most observers see only stacks of simple rectangles, unaware of the careful agreements and technical documents that keep those rectangles aligned. The significance of these standards lies not in dramatic change, but in steady continuity. They allow ships to be designed with consistent bays, cranes to be built with reliable outreach and lift patterns, and yards to be arranged in repeating grids. Even as new trade routes emerge and older ones decline, the standardized container provides a constant reference point. Engineers, planners, and operators make daily decisions within this framework, often without reflecting on its origins. Yet the influence of ISO 668 and ISO containerization is present in each container that is loaded, stacked, and secured in its place. The result is a global system that appears ordinary and repetitive, but rests on a quiet foundation of shared measurements and practices. Thanks for joining us for Standardization and History of Shipping Containers and ISO Containerization. If you are still awake, please stand by for our next program.